Okay, so this is 2013, question 7 on rates of reaction. These questions tend to repeat themselves quite a bit, so probably if you do this early in the week, you will have answered these exact questions again by the end of the week. Okay, so it's just all about practicing these questions because they do repeat. Rates of reaction comes up every year, so it's an easy place to get marks. Okay, so the first few parts are just theory based basically from your notes. So define the rate of a chemical reaction, so the change in concentration of your reactants or your products over time. Okay, explain clearly why there is an almost instantaneous reaction between aqueous solutions of sodium chloride and silver nitrate. The reason there is that they are ionic compounds. Okay, ionic compounds or reactions involving ionic compounds take place instantaneously, whereas covalent compounds take a little bit longer to for the reactions to take place. Okay, so ionic compounds, they're there that the ions are free. Okay, but ionic compounds is enough to have there. Okay, when hydrogen gas and nitrogen are mixed in a ratio of 3:1 by volume at room temperature in a sealed container, the formation of ammonia is very slow. Suggest 2 ways to increase the rate of reaction. So you're just looking at your factors that affect rate of reaction and what would increase that rate. Okay, so here if we increase the temperature, okay, if we increase the temperature, then the molecules have more energy, so more molecules reach your activation energy, so more effective collisions can take place. If we increase the concentration, or seen as we're working with gas, if we increase the pressure, then your molecules are closer together and more effective collisions are likely. So they would be our two reasons. The other one you could have there is the addition of a catalyst. Okay, and your catalyst reduces your activation energy. So there are 3 ways of increasing the rate of reaction and an explanation for each. So part D then, describe how you would measure the reaction time when 10 centimeters cubed of 1 molar hydrochloric acid solution and 50 centimeters cubed of 0.2 molar sodium thiosulfate solution react according to the following balanced equation. Okay, so there, that's actually an experiment we do. So we are going to put your thiosulfate solution over an X on a white surface. Okay, so if we just zoom out, above there are the answers for the other questions also. Add hydrochloric acid and records the time it takes for the X to become invisible using a stopwatch. Okay, so yeah, that should be pretty simple enough, I hope. It's an experiment we did. I think it was actually the first experiment, one of the first experiments we did when I came to the school. And then if you were given an additional sodium thiosulfate solutions with the different concentrations that are listed there, describe how you would show that the rate of reaction is directly proportional to the concentration. So what you do there is you repeat the same procedure for the different concentrations, and then you calculate 1 over T. So you put 1 over your time, okay, and you graph those figures, the 1 over T, against your concentrations. Okay, then you calculate your rate constant, okay, K. Okay, to do that you just put your rate over your concentration. Okay, for each of the different concentrations. Okay, and then when you graph those figures, if you graph rate versus concentration, your straight line will go through the origin. So if you graph rate versus concentration, you will get a straight line. Okay, and that shows that it's directly proportional. Okay, so straight line through the origin for your graph of rate versus concentration shows that they are proportional to each other. And then part E. Draw a reaction profile diagram for an exothermic reaction, indicating clearly on your diagram the activation energy and the heat of reaction. Okay, so if we put in our axes, okay, on the x-axis we're going to have time, and on our y-axis we have energy. Okay, it asks us for an exothermic reaction, so that means our reaction is going to have less energy at the start than, less energy at the end than it had at the start. So you're starting with a certain amount of energy and you're finishing with less. Exothermic reactions give off energy, okay, or lose energy. Okay, so we're going to start with a certain amount of energy. Okay, so that's where our reactants are. Okay, so we have that much energy at the start in our reactants. Then in order for the reaction to take place, we have to, our energy will increase. Okay, I'll just zoom in a bit. Okay, and then we end up losing energy because it's an exothermic reaction. Okay, so this would be an extremely exothermic reaction. Okay, but it's better to make it obvious that there's less energy at the end than there is at the start. Okay, rather than having it questionable, I suppose. Okay, so our activation energy here is from the energy that's in our reactants. Oops, got a different pen. So it's the energy that's in our reactants, between that energy and the very top of our graph. Okay, there we go. Alright, so it's going to be in there. Now, it's extremely important that when you're marking this activation energy, that this line or this arrow touches the top of that graph. If that does not touch the top of that line, or that line at all, you will not get the marks. Okay, they're even becoming strict on this at Junior Cert. That was actually a question on the Junior Cert last year, and people drew the line. They knew where the activation energy was, but they may have only gone as far as here, where that green dot is. And even though the examiners knew that the person knew what the activation energy was and that they indicated it, because the line did not touch the top of the graph, and they did not get the marks. Okay, so make sure that arrow touches the top of that graph. Okay, so that's your activation energy. Okay, and your heat of reaction then is the difference between the energy you had at the start and the energy you had at the end. So your delta H is going to be, oops, it's big. Okay, so that's going to be your delta H figure. Alright, so your delta H is the difference in energy from the beginning to the end. Okay, and that is 2013 question 7.